Hi everyone, my name is Farah, and today I'll be representing the biomedical research team of Hyperlink at Queen Mary University of London. I would first like to start by thanking all the other teams that have presented and are still going to present. I found it very interesting to look at all the different aspects that we're considering for the Hyperloop transportation system and how teams are looking at how to build it and how it affects different aspects of and different countries. But today I'm going to be looking at a different aspect. I'm going to be looking at how the Hyperloop transportation systems will affect humans and how to ensure that it's a very safe system for humans and that it's safe for humans to travel in it. So my team has been looking at researching and designing a suitable electromagnetic shield for the Hyperloop transportation system to ensure that that no negative effects affect the humans while they're traveling on the Hyperloop transportation system. So first, I want to look at propulsion systems and aviation systems. So our propulsion teams have been looking at possible propulsion systems, and they came up with 4 potential systems that could be used. So the first one is the linear induction motor, the second one is the electrodynamic wheels, the third one is the electromagnetic suspension, and the last one is the linear hallback arrays. So after the propulsion team has conducted a lot of research, and read a lot about the Hyperloop, they have decided that the linear induction motor is the most suitable system for the Hyperloop transportation. And that's why we based most of our research and most of our simulations on that system. So we did a lot of studies and read a lot of research papers to try to understand how the linear induction motor runs using electromagnetic and how the electromagnetic radiation that emits from those systems will affect the humans, and how to ensure that those radiations do not negatively affect humans, to ensure that the Hyperloop is safe for humans and therefore ensure that the technology and the studies of the Hyperloop is actually useful. So to further understand the electromagnetism and the electromagnetic concepts and the electromagnetic radiation that emits from the propulsion systems, we had to first look at fundamental concepts and have a better understanding. So to do that, we looked at 3 different things. So the first law we looked at was Faraday's law, and that is an electromagnetism law that predicts how electromagnetic fields interact with electric currents to produce electromotive force. It also looks at how the electromotive force is produced when there's a change in magnetism. Next, we looked at Lenz's law, and this law is used to detect the direction and show the fluctuation in the magnetic flux due to the pre-existing electromagnetic fields within the Hyperloop propulsion system. Last, we looked at correlation between electromagnetic flux density and frequency, and when we did our research, we found an equation that correlates those 2 variables. And this will be extremely important later on when I start talking about the simulations we've run, because our simulations use electromagnetic flux density to compare the distance. And when we were studying how different when radiations affect different systems within the human, we looked at different frequencies and the effect of those frequencies on human. Therefore, we need this equation to see how the density that the electromagnetic flux density that humans will be exposed to will have an effect on humans, and to see which frequency those humans will be exposed to ensure safety for those humans. So as I mentioned before, the electromagnetic radiation emitted has effects on different systems within the humans. So the first system I'll be talking about is the cardiovascular system. And as we all know, the heart is one of the main organs within the body, and its main function is to pump blood throughout the body. So the heart maintains homeostasis by using physical features such as contractibility and inductibility. And a lot of research papers have proven that when humans get exposed to electromagnetic radiations and the body absorbs those radiations, the inductibility factor within the body can be affected, and this can change the heart rhythm within the human body, and this can lead to serious disease such as heart attacks, which could negatively affect humans. Next, we looked at tissues and organs. It was proven that when electromagnetic radiation is absorbed, this can have a thermal and a non-thermal effect. So the body can absorb, the skin and different organs within the body can absorb the non-thermal effect, which can cause an increase in temperature within the brain and different other organs. This can lead to the death of many cells, which can negatively impact the body and the functions of the body. Next, I looked at the reproductive implication. Next, we looked at the reproductive implications, and it's been proven that when the radiation is absorbed within the body, this can lead to decrease in sperm motility, which means that the sperm will not be able to move as they usually would, and this indicates that there could be a reduction in the chances of humans reproducing. And therefore, this has a really negative effect on humans, and also this will reduce the number of humans that could possibly be born later on. We also looked at cognitive effects, neurological effects, musculoskeletal effects, respiratory effects, and nausea, vertigo, dizziness, and metallic taste. And all the research papers we've read and all the research that have been done showed that electromagnetic radiation can have a hugely negative effect on humans and those systems. So due to those negative effects, we had to come up with a solution to ensure that like humans are safe and there are no negative effects within the humans, and all those negative effects that I've previously talked about are the risks of those effects happening are as low as possible. So we came up with a solution, and that solution is to use a magnetic shield around the pod, and this will ensure that the electromagnetic waves that enter the pod are as safe as possible for humans, and no negative effect can cause, and no like frequency that is dangerous for human can enter the pod. So I'll start explaining. So here we have the electromagnetic waves that emit from the propulsion system, and the blue box is our magnetic shield. So what we expect the shield to do is to reflect some of those electromagnetic waves and absorb some of them. And then this is basically, those two factors are used to calculate the magnetic shield effectiveness. So the higher the reflected loss and the higher the absorption loss, this means that we have a good magnetic shield. And we want to ensure that the transmitted electromagnetic waves are as low as possible and also are within a safe frequency that would not negatively affect the humans in any way. So to come up with those solutions, we looked at different electromagnetic concepts, and those are the electromagnetic interference, the electromagnetic shielding, and Shkalkon's theory, and those theories helped us come up with our solution. So next, we looked at different materials that could be used for the electromagnetic shield due to their good mechanical features. So the first material we looked at was aluminum, and the main reason we chose aluminum as a potential option was because it has non-magnetic properties and high conductivity, which means that it should ensure that no dangerous electromagnetic waves enter the pod and ensure the safety of humans. Next, we looked at copper. And why did we choose copper? We chose copper because it has high thermal and electric conductivity, which again ensures that it absorbs and reflects the most amount of magnetic waves and doesn't let a lot of magnetic waves enter the pod, therefore ensures that humans are as safe as possible. And last but definitely not least, we looked at copper alloy 770. And why did we choose it as a potential material is because of its corrosion resistant properties and high magnetic permeability, which again ensures that the amount of magnetic waves entering the pod are as low as possible. So we ran simulations using CST software to test our theories and to test the materials and to ensure and to come up with the results of which material is best to use. So as you can see here, the yellow bit is our magnetic shield, and it's cylindrical shaped and located centrally between the propulsion system, and this colored bit is our propulsion system. So when we were running those tests, we ensured that all the variables were kept constant except the material. So the size of the magnetic shield, the location in relation to the propulsion system, and the voltage that's running through the system has been kept constant throughout the testing. The only thing that has been changing is the material. And for all the three materials, the thickness of the material was 90 millimeters. So the two factors that we're comparing here is the electromagnetic flux density, and this kind of indicates the strength of those magnetic waves that emit from the propulsion system. And using this, as I mentioned before, we're going to use the equation to kind of test the frequencies, and then we're going to kind of show how those frequencies affect humans. So we're going to test how safe those electromagnetic flux densities and those electromagnetic waves that the humans are going to be exposed to. And in comparison, we compared the electromagnetic flux density which also is measured in Tesla, against the cross-sectional distance in millimeters. And this is the distance from the propulsion system. So the further we go from the propulsion system, the higher the number will be, because the distance between the propulsion system and the emitted waves is going to increase. So first we tested aluminum. So on the y-axis, as mentioned before, it's going to be the magnetic energy density measured in Tesla. On the x-axis is the cross-sectional distance measured in millimeters. So as we are expecting, in the middle we have the highest magnetic energy density, because we have the least amount of distance between the propulsion system and the waves, and therefore the waves we gain are very close, are just emitted from the propulsion system, which means they have really high power because they haven't traveled enough to like lose their strength. And as we see here, as we go further away from the propulsion system, we experience a decrease in the magnetic energy density, as you can see here. Next, we tested copper, and also, as you can see, like I mentioned before, in the center, we're going to be expecting the largest number of the largest value of magnetic energy density. And as we go further away, we are experiencing decrease in the magnetic energy density. And we followed the same simulation for copper alloy 770. Again, same concept. So in the end, we found that the best two materials are copper and copper alloy 770, but we compared those two to conclude which material is the best material to use. And what we found is that copper alloy 770 is actually the best material, because as you can see here, the decrease is much steeper than in copper, which indicates that the electromagnetic waves, they lose their power faster, and therefore they don't affect humans as much as they would if we had copper as a magnetic shield. Also, you can see here that magnetic energy density reaches 0 Tesla at a less distance than here. Here you can see that it reaches around 420. Well, here it reaches around 330. Therefore, it indicates that copper alloy is the best magnetic shield material out of those three options. So looking more to copper alloy, so copper alloy is made of 55% copper, 27% zinc, and 18% nickel. And we calculated the cost per ton for copper alloy, which turned out to be 13,813.35. As you can see, nickel has the highest cost, and our team is currently looking at how we can reduce this cost by using different concentrations of zinc and nickel to reduce the cost. By using different concentrations of nickel, and by doing that, we can kind of reduce the cost. We're also running simulations against COMSOL, which is a better software that will lead to more accurate results. And throughout our research, a lot of research papers have been saying that magnetic shield is not necessary for Hyperloop, and that humans are still going to be safe. And some research papers are saying the opposite, and they're saying that having a magnetic shield is essential. And therefore, our team has decided that we should have a magnetic shield, because as I mentioned before, safety of humans is the most essential and the most important cause, and we need to ensure that all the humans from different age groups and all different humans are as safe as possible. Thank you, and I'm happy to answer any of your questions.
Cool. Does anybody have any questions at all? Yeah, it's really cool. I think you guys are the first Hyperloop team to ever kind of venture into that kind of side of things. So that's really awesome. Are you guys planning on getting the paper published?
Yeah, we're also writing 2 other papers. One about the ergonomics, so like how the seating is going to be, and then we're also talking about the vacuum and the effect on vacuum of because you know how we're going to travel in the vacuum, so we're going to test that and how it affects humans and all of that, which is really important, because I feel like we might be doing a lot of studies, but in the end, like we need to ensure that humans are safe, you know.
Yeah, I mean, because you can just see from this weekend how everybody's so focused on like making the pod itself and like making the technology, but there's really so many other considerations that we need to think about. So I'm glad you guys are thinking about it.